Alright, so in the last section we looked at power series and we discussed what is the radius of convergence and interval of convergence for those power series. Remember, the interval of convergence is represented by this capital I, and the radius of convergence is represented by this capital R. Okay, and so generally our technique was to apply the ratio test and we could determine those things. Now, another thing that we did that I think was significantly easier was we identified the coefficients, right, that C sub n of our power series, and we determined the center of the power series, right? So we have x minus a to the n, and a gave us the center of the power series. In this section, we're going to be trying to take f of x functions and find a power series representation for them. A lot of the times what we're going to do here is we're going to use properties of the geometric series. So remember that for a geometric series, we know that if we have something that looks like this, then it's going to converge to a over 1 minus r. Right? Remember, this was a over 1 minus r. And so here our a is 1, and then our r would be just x. Right, because remember, we should have something that looks like sum from n equals 0 to infinity of a times r to the n. Right, and so if this r has absolute value less than 1, then we know that this converges, and furthermore, we know that it converges to this. So that tells us that the interval of convergence must contain this interval, and that the radius of convergence would be 1. Now, if we test the endpoints for convergence, right, if we plug in -1 for x into this power series, or if we plug 1 in for x into this power series, then we will find divergence at both endpoints, and by the test for divergence. So let's take some different functions and see if we can find the power series representation. Okay. So, we know that geometric series converge to a over 1 minus r. And so if we set this equal to our function, 1 over 1 minus 3x, then we will get a equals 1, and r will be equal to 3x. So we can say that f of x is really equal to the sum from n equals 0 to infinity of a times r to the n. So this would be 1 times 3x to the n. Now, we know that this will converge, so this converges if the absolute value of r, so the absolute value of 3x, is less than 1. Which means that we'll need -1/3 to be less than x, which should be less than +1/3. Okay. So then this tells me that my radius of convergence will be -1/3. Or sorry, my radius of convergence is going to be 1/3. And then my interval of convergence will be -1/3 to 1/3. And here, if we plug in either one of those into our series, we're going to get that they would diverge. So it turns out that this is not saying I is at least this interval. I is exactly this interval because the endpoints do diverge. Okay, now let's look at example 2. So this one's a little bit harder because it doesn't look like it's in the form of, a over 1 minus r. So what I'm going to do is I'm going to note that 1 over 5 plus 4x is the same thing as 1 over 5 times 1 plus 4/5 x. Right, so all I did was just factor a 5 out of that. Now I can say that this is 1/5 over 1 plus 4/5 x. And so here, I'll get my a value. Now remember, this is supposed to be 1 minus r. So that means that r will be equal to negative 4/5 x. Okay. So then our power series representation, we can say that f of x is going to be equal to the sum from n equals 0 to infinity of, this should be a times r to the n, so this will be 1/5 times r to the n, so this will be 4/5 x to the n. Sorry, negative 4/5 x to the n. Okay. Now, if I wanted to make this look like an actual power series, because remember our actual power series look like c sub n times x to the n, then I could rewrite this as n equals 0 to infinity of, let's see, we would have 1/5 times negative 4/5. That's a 4, not a 9. Times x to the n. Right, and so then this would be my c sub n. Okay, that'll show up later. For now, let's worry about finding our radius of convergence and our interval of convergence. So we know that this thing will converge if the absolute value of r is less than 1. So we need the absolute value of negative 4/5 x to be less than 1. Which means that I need negative 1 to be less than 4/5 x, which should be less than 1. Which means that I need negative 5/4 to be less than x, which should be less than positive 5/4. So this will tell me that my radius of convergence is going to be 5/4, and that the interval of convergence will be negative 5/4 to 5/4. Okay, now example 3 will be quite a bit harder. The best way to look at example 3 is for us to notice that x over 2 minus x squared is equal to x times 1 over 2 minus x squared. Well, this can be simplified a little bit more. What I'm trying to do is I'm trying to get something that looks like 1 over 1 minus r. Right, if I have 1 as my a on top, then it makes my power series a little bit easier to work with. So this could be written as x times 1 over 2 times 1 minus x squared over 2. Okay, well this is the same thing as x over 2 times 1 over 1 minus x squared over 2. And so now what I'm going to do is I'm going to represent this part with a power series. Right, so this, what I've circled in red, this would be equal to the sum from n equals 0 to infinity. Well, let's see, our a is this part, that's a. And then our r is sitting right here. So then this is going to be x squared over 2 to the n. And so what I can say here is that f of x is equal to x over 2 times this power series, so this sum from n equals 0 to infinity of x to the 2n over 2 to the n. Right, all I've done there is just distributed that power of n to the top and bottom of the fraction. So then this becomes the sum from n equals 0 to infinity. Well, let's see, if I'm multiplying this with an x on top, then this becomes x to the 2n plus 1. And if I'm multiplying with a 2 on bottom, then this will be 2 to the n plus 1. Okay, so notice this is the same thing as the sum from n equals 0 to infinity of x squared over 2 to the n plus 1. Now, remember that we want this to be in the form of a times r to the n. So we'd technically have to factor an x squared out of 2 to get this in the right form. An x squared over 2. But that's not going to change the value for our r. No matter what we have to factor out, r is still going to be x squared over 2. So we want the absolute value of x squared over 2 to be less than 1. Well, this thing, the absolute value, really isn't doing anything here, because x is getting squared on top, so that'll be a positive number on top. And then we'll have a positive 2 on bottom, so there's no way this thing can be negative. So this means that x squared over 2 has to be less than 1, which means that x squared has to be less than 2, which means that x has to be less than square root 2 and greater than negative square root 2. Right? Anything in that area will make x squared less than 2. So that tells me that my radius of convergence is going to be square root 2, and that the interval of convergence will be negative square root 2 to square root 2. So this is why geometric series are nice, because we don't have to go back and test these endpoints every single time to see if something different's happening. Every time you get an endpoint, you're going to end up getting basically your r right here will become 1. And so you're just going to be summing some positive number over and over again. Or if we have a negative, we're going to get that the alternating series test would say that it that the test for divergence will say that it fails. Okay. Now let's look at this new theorem. So this theorem is dealing with what happens when you take the derivative or the integral of a power series. So here's what's happening here. If we have this power series, c sub n times x to the n, and it has some radius of convergence r, then f prime of x, right, the derivative of this power series, is going to have the same radius of convergence, and it can be written like this. So let's see what's happening here. This power series right here, this is going to be equal to, let's see, we'd have c sub 0 times x to the 0, so that's just c sub 0, plus c sub 1 x to the 1, plus c sub 2 x squared, plus c sub 3 x cubed, and so on. So then that tells me if I take a derivative of this thing, f prime of x, well, when we take the derivative of this constant right here, it's going to disappear. When I take the derivative of c sub 1 times x, remember c sub 1 is just some coefficient, some constant coefficient, then this is going to become just c sub 1. If I take the derivative of c sub 2x squared, that would give me 2 c sub 2x. And then we'd have 3 c sub 3 x squared, and so on. So notice that this is, I can write this sum, so I'm starting with c sub 1, so that's why I'm starting at n equals 1 to infinity. And so this would be c sub n times x to the n minus 1. Right, if I do that, that'll give me right? My c sub 1, my c sub 2x, my c sub 3x squared. But what I'm missing is this other coefficient right here. And so what we have to do is we have to multiply this by n. And that is exactly what we have right here. Now, if I want to change this into a power series where we start at n equals 0, if I'm going from a sum of n equals 1 to n equals 0, then what I need to do is we need to add 1 to all of our n's, right? So here I'm going to add 1 to this n, so that'll give me, let's change this to a 0. So if I add 1 to that n, that gives me c sub n plus 1. I'm going to add 1 to this n up here, so that'd be n plus 1 minus 1, so that would just become n. And then we'd have times n plus 1. Okay? So that is how you remember that when you take the derivative of a power series, what you're going to do is you'll add 1 to your n values, and then we'll need to multiply by n plus 1. Okay. And we'll look at applying this later, but this is going to be super, super important. Now, for integrating this, right, so now let's look at what happens when we integrate. I'm still going to keep this circled because it's just so important. Okay, now let's look at what happens when we integrate this. Whenever we integrate, right, we always get this plus c. So I'm going to leave my big C out in front. Now if I integrate c sub 0, that should give me c sub 0 times x. If I integrate c sub 1x, that should give me c sub 1 x squared over 2. If I integrate c sub 2x squared, that should give me c sub 2x cubed over 3. And then so on. And so notice what's happening here. We have this plus c out in front. And then the rest of this can be written as, well, let's see, the sum from n equals 0 to infinity. So I start with c sub 0, so it tells me I want to start with c sub n. And then I'm multiplying by x. So that's times x to the n plus 1, because 0 plus 1 will give me x. And then I'm going to divide by n plus 1. Okay, so notice if I look at this part right here, right, if we plug 3 into this if we plug 2 into this formula, I would get c sub 2 x squared, or x cubed on top, just like we have up here. And then on bottom, we would get 2 plus 1, which is 3, just like we have right here. So whenever we're integrating, what we're doing is we're adding 1 to the exponent of x, and then dividing by that exponent. Okay, so this is super important as well. And it's also important that I said we're dividing by that exponent, okay? We'll look at that later, what's happening there. So let's look at example 4. Here I want to identify that c sub n is equal to n plus 1 over n factorial. Right, and so now we can write this as c sub n times x to the n, right? A proper power series. So let's say we're taking the derivative of this. Well then f prime of x, this should be the sum. Oh, actually before I start this, I want to go over these notes real quick. Whenever you for the first note, whenever you differentiate a power series, it says the starting index will change if the first term is constant. So what that's saying is if somehow, right, if this was, say, c sub n times x to the n plus 1, then what this would look like would be c sub 0 times x plus c sub 1 x squared plus c sub 2 x cubed, and so on. So here, the starting index wouldn't have to change. The reason it doesn't have to change is because we want this c sub 0 to be in there. When we take a derivative of this, we're still going to have a c sub 0. It won't disappear like it did last time. Okay, so in this case, we wouldn't have to worry about our starting index changing. Now, when you integrate a power series, the starting index will never change, meaning we don't have to worry about does it start with a constant or not. Okay, now let's look at example 4. I'll leave this formula up here so that we can refer to it. Okay, so our formula says that this should be the sum from n equals 1 to infinity. First, I want to check and see, okay, should my starting index change? Meaning, should it start at n equals 1? Well, if we look at this power series, this is going to be times x to the n. So we'll have a c sub 0 plus c sub 1x plus c sub 2x squared, and so on. And so when I take a derivative here, this c sub 0 will go away. So yes, we do need to start at the sum from n equals 1. Okay, so my formula says this should be c sub n times n times x to the n minus 1. And so now, to change that to a sum that starts at n equals 0, I'm going to add 1 to all my n's. So this would be c sub n plus 1 times n plus 1 times x to the n plus 1 minus 1, which is just n. And so now if I plug everything in, this is going to be the sum from n equals 0 to infinity. C sub n plus 1, so that would be n plus 2 over n plus 1 factorial. Right, because all I did is I took this n plus 1 and I plugged it in for the n's in this c sub n. And then we should have times n plus 1 times x to the n. Okay, so that would be the derivative of this power series. Now we can actually simplify this a little bit more. So notice that I could have written this as kind of like one big fraction. Okay, and so here we would get, well, let's see, n plus 2 times n plus 1. Now the bottom, n plus 1 factorial, is the same thing as n plus 1 times n factorial. So then this would be the sum from n equals 0 to infinity of n plus 2 over n factorial, right, because we can cancel these guys out, times x to the n. Right, and so this would be our derivative of our power series. Now let's look at integrating our power series. So I'll use a color that we're all fond of. Right, so the integral of f of x. Okay, well, our formula, I can scroll up just a little bit, says that this should be c plus the sum from n equals 0 to infinity of c sub n over n plus 1 times x to the n plus 1. So this would be c plus the sum from n equals 0 to infinity. Let's see, c sub n was n plus 1 over n factorial. So let's see, we have n plus 1 over n factorial divided by n plus 1 times x to the n plus 1. So then this becomes c plus the sum from n equals 0 to infinity of, well, let's see, our n plus 1s would cancel out, so we'd be left with 1 over n factorial times x to the n plus 1. Okay. So that's our first steps in solving for integrals and derivatives of power series. Alright, now let's look at the next problem. So this next problem really isn't as simple as the previous problem, because our f of x function, right, this 1 over 1 plus x to the 6th, hasn't been given to us as a series. So what I want to do is I want to convert it into a series. So I'm going to call this fraction right here, this is going to be f of x. So I can say that f of x is equal to, well, here my a value would be 1, my r value would be negative x to the 6th. So I can call this the sum from n equals 0 to infinity of negative x to the 6th to the n, which would be the same thing as just writing this as the sum from n equals 0 to infinity of negative 1 to the n times x to the 6n. Okay, now what I'm going to do here is I'm going to identify my c sub n, so this would be my c sub n, and then we're going to use our integral formula. So we're going to do the integral of our f of x, so this is the integral of n equals 0 to infinity, negative 1 to the n, times x to the 6n dx. So this would give us c plus the sum from n equals 0 to infinity. Now remember, our formula for this is that we should have c sub n times, we should add 1 to our exponent of x, so this should become x to the 6n plus 1, and then divide by that new exponent. So remember, this is really just our integral rules for powers, right? Whenever we have something like x to the 4th and we integrate it, we add 1 to the exponent and divide by it. So I'm keeping the constant the same, right? Because in integrals, we can pull out the constant. I'm adding 1 to my exponent of x and then dividing by that new exponent, right? And so this is really equal to c plus the sum from n equals 0 to infinity of negative 1 to the n, right? Because that was our c sub n, times x to the 6n plus 1 over 6n plus 1. Alright, now you may stop here and take a break, whatever you want to do. This has covered everything that you'll need for Wednesday's class activity. If you'd like to keep watching, you can, but everything that comes after this and in the next video will be for Friday's class activity. Thank you. Alrighty, now let's move on to example 6. Alright, so for example 6, we're asked to find the power series representation for this function and determine the radius of convergence. Okay, so I'm actually going to, let's see, we can find the radius of convergence. So the first thing I want to note in this problem is that this f of x, this is really the same thing as 1 over 9 plus x squared. Alright, so here's the note. Here's the trick. If you see 1 over something squared, integrate it first. Before you do anything, just integrate it, okay? So let's see, if we're following that rule, then the integral of 1 over 9 plus x squared dx. This should give you negative 1 over 9 plus x plus c. Now something's going to happen here. Later on in this problem, right, we can't just integrate something and say that it's the same. So later on in the problem, whatever power series I'm getting, I'm going to have to take a derivative of it, right, so that we can cancel out this integral we just did. So what I'm going to do is I'm going to omit this plus c, because when we take a derivative of it later, it's going to disappear anyways. Okay, so this is going to be equal to negative 1 over 9 times 1 plus x over 9. So this is the same thing as negative 1/9 times 1 over... So if I want to write this in the form of 1 minus r, then this would be 1 minus negative x over 9. Right, because notice that the two negatives would cancel out, so we'd get our positive x over 9 like we had before. So this is the same thing as negative 1/9 times the sum from n equals 0 to infinity of, well, let's see, we take our r value, negative x over 9, raise it to the n. And so this would be the same thing as the sum from n equals 0 to infinity of negative 1/9 times, well, let's see, this would be negative 1 to the n, x to the n, over 9 to the n, which is going to be equal to the sum from n equals 0 to infinity of, well, let's see, if I multiply the negative 1's out, then we'll get a negative 1 to the n plus 1. We'll have a x to the n, and then on bottom we'll have a 9 to the n plus 1. And so my c sub n is going to be this part right here. All right. Now, like I said before, we need to get rid of this integral we just did. So what we're going to do is we'll have the derivative, d dx, of the integral of 1 over 9 plus x squared. Oh, sorry, that's why this looks so funky. This should have been squared out here, right? Just like we have here. Okay. And so what's happening here is that this derivative and this integral will cancel out. So we'll have our f of x that we originally started with. Okay. Well, this is the same thing as d dx of, well, we know the integral of this, we represented that right here. So this is d dx of the sum from n equals 0 to infinity of negative 1 to the n plus 1 times x to the n over 9 to the n plus 1. Okay. So then by our rule for derivatives on series, we'll get 1 over 9 plus x squared is equal to, alright, so let's look at this. This is a x to the n. So when we start at n equals 0, we're going to start this series out with a constant. So that means I need to start with the sum from n equals 1 to infinity of, alright, so remember, we'll have our c sub n, negative 1 to the n plus 1, over 9 to the n plus 1, times n, times x to the n minus 1. All right, so remember our derivative rule was that, let me go back. Right, we kept c sub n the same right here. We multiply by n, and we subtract 1 from the exponent of x. Right, and so that's exactly what I did here. I kept this c sub n the same. I multiplied by n, and I subtracted 1 from the exponent of n. Now I want to make this a power series, so I want it to start at n equals 0 to infinity. And so that means I need to add 1 to all of my n's. So this will become negative 1 over 9 to the n plus 2 times n plus 1 times x to the n. Right? So that is my power series representation for this f of x that we were given. So notice how, right, my first step here was to integrate because I saw 1 over something squared. And so I integrated it, I got a power series representation, I identified the c sub n, and then I went back and took the derivative of both sides. Right, so when I take the derivative of the left-hand side, we get our original starting function. When I take the derivative of the right-hand side, I'm taking the derivative of this power series that I found and just using our rules from that theorem. Okay. So let's try a similar problem. Here I don't see 1 over something squared. However, I can write this as f of x equals x squared times 1 over something squared. Now that I've done this, I'm going to just focus on this part and try to represent it as a power series, and we can multiply this x squared back in later. Okay, so the integral of 1 over 1 minus 2x squared, that would be equal to 1/2 times 1 over 1 minus 2x. We should have the plus c, but we know we're going to take a derivative later on, so the plus c doesn't really matter. If you're wondering where I'm getting these integrals from, I'm doing u sub on our denominator, not including that exponent of 2. Okay. So then this should be equal to 1/2 times the sum from n equals 0 to infinity of my a times r to the n. Well, a is 1, right? There's my a value. And then my r will be positive 2x, so this is 2x to the n. Alright. So then this is the same thing as the sum from n equals 0 to infinity. This would be 2 to the n, x to the n, and then multiplying out that 1/2, we have divided by 2. So this is really just, I can just subtract 1 from the exponent of 2, so we have 2 to the n minus 1 times x to the n. Okay. Now, just like before, we're going to take an integral of both sides. Right? Remember, we haven't worked with this part yet. We'll work with this later. I'm still just working with the part that I circled in red. So we'll have d dx of the integral of 1 over 1 minus 2x squared. I'm forgetting dx is in here. So this will be equal to d dx of the sum from n equals 0 to infinity of 2 to the n minus 1 times x to the n. So remember, here's my c sub n. Okay, and so what I'll need to do is this will be 1 over 1 minus 2x squared. I'm again messing this up. The square needs to be outside. Alright, so our derivative and integral cancel with each other. And then on the right hand side, this is going to be the sum from n equals 1 to infinity. Just checking real quick, we have an x to the n here. So that does mean that we'll start this series off with a constant. So that's why I'm starting at n equals 1 to infinity. And then this should be c sub n, which is 2 to the n minus 1, times our exponent of x. So this is times n, times x to the n minus 1. Okay. And so then if I want to change this to a starting index of 0, then this is 2 to the n times n plus 1 times x to the n. Okay. So now we'll go back to where we started. F of x is going to be equal to x squared times 1 over 1 minus 2x squared. Well, 1 over 1 minus 2x squared is really equal to this right here. So I'm going to substitute that in. So times the sum from n equals 0 to infinity of 2 to the n plus 1, x to the n. And so when I multiply out that x squared, we'll get the sum from n equals 0 to infinity, 2 to the n plus 1, x to the n plus 2. Because I can just add these exponents right here. Okay, now we need to find the radius of convergence here. Well, for the radius of convergence, we can do our ratio test. Oop, wrong color. Okay, so for the ratio test, we'll have the limit as n goes to infinity of, 2 to the n plus 1, n plus 2, x to the n plus 3, over 2 to the n plus 1, x to the n plus 2. Right, and then we'll need to take an absolute value. Alright, well this is going to be equal to, 2 to the n plus 1 divided by 2 to the n. That's just 2. So I can get rid of that. Now, this part right here, different color please. This part right here is going to go to 1. I don't want that 3 to be next to it. It's not going to 13. Right, this goes to 1. And x to the n plus 3 over x to the n plus 2, well, that's just really equal to x, because we subtract exponents. So really, this is going to be equal to the limit as n goes to infinity of the absolute value of 2x, which we want, remember by the ratio test, we want this to be less than 1. So that means that negative 1/2 is less than x, which is less than positive 1/2. Okay, which tells me that my radius of convergence is going to be 1/2. Okay, now let's move on to example 8. For example 8, I'm going to introduce a new rule to you. If you see the natural log of a sum, right, so even if you see subtraction in there, you'll have to be concerned about where your power series is centered. So we'll focus on just sums inside of this natural log. But see how here we have a sum. We have 3 plus x. If you see something that looks like this, then you should differentiate first. Okay, let's see why. If I do that, well, d dx of the natural log of 3 plus x will be equal to 1 over 3 plus x, which is the same thing as 1/3 times 1 over 1 plus x over 3. And so this is going to be equal to, we should have 1/3 times the sum from n equals 0 to infinity of, we get, remember our r right here is going to be negative x over 3. So this is going to be negative x to the n over 3 to the n. So this will be the sum from n equals 0 to infinity of negative 1 to the n times x to the n over 3 to the n plus 1. So now I'm going to integrate both sides. So let's see, the next step, we'll do it in a different color. I'll take the integral of d dx of ln of 3 plus x dx. And then I'll take the integral of the sum from n equals 0 to infinity of negative 1 to the n x to the n over 3 to the n plus 1 dx. Okay, so that will give us that the natural log of 3 plus x is going to be equal to, well, remember our rule for integrals, our starting index does not change. We have n equals 0 to infinity of, now we have to add 1 to our exponent of x and then divide by that exponent. So this stays as negative 1 to the n. We add 1 to the exponent of x and then divide by that new exponent. So that means I'm going to multiply 3 to the n plus 1 with n plus 1. And then we should have a plus c. Now, what if we want to solve for this plus c? Well, if we let x equals 0, on the left-hand side, I'll get ln of 3 plus 0, so it's just ln of 3. And this should be equal to the sum from n equals 0 to infinity of negative 1 to the n. Plugging in x equals 0, I'll get 0 to the n plus 1, which is 0, over 3 to the n plus 1 times n plus 1. And so notice we'll get a 0 on top here, and 0 divided by some non-zero constant is just going to be 0. So this actually goes away, and we get ln of 3 equals c, which tells me that my representation for ln of 3 plus x, we get ln of 3 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the n x to the n plus 1 over 3 to the n plus 1 times n plus 1 plus ln of 3. Okay. Now let's try example 9. Example 9 looks tough, but we can actually use the previous example to do this. And in fact, whenever we're looking at x times the natural log of a sum, what you want to do is you want to start with just the natural log of the sum. Just work with that, right? Because notice that this part right here is what we did in the last problem. So if you just focus on this part and you'll get this junk, then we can say that f of x is equal to x times the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over 3 to the n plus 1 times n plus 1 plus ln of 3. Right, so x is being multiplied with all of this. Let me draw that a little bit better. Okay, and so then this gives us the sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 2, over 3 to the n plus 1 times n plus 1, plus x ln of 3. Okay, now the next part asks us for the integral of this. So what I'm going to do is I'll write this as the integral. So let me scroll over just ever so slightly. I'll write this as the integral of what we just got in the previous problem. So the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 2 over 3 to the n plus 1 times n plus 1 plus x ln of 3. Okay. So for the first part, for this series, whenever we integrate it, remember we're going to add 1 to the exponent of x and then divide by that exponent. So that'll give me the sum from n equals 0 to infinity, negative 1 to the n times x to the n plus 3 over 3 to the n plus 1 times n plus 1. And remember, I have to divide by this new exponent. So I'm multiplying the bottom by n plus 3. Plus, now we need to integrate this part. So ln of 3 is just a constant. So the integral of x ln of 3 will give us x squared ln of 3 over 2 plus c. Okay. Now let's move on to example 11. Example 11 asks us to find a power series representation for f of x equals arctan of x. Okay. So here's what I want to start with. We know what the derivative of this thing is, right? The derivative is not bad. We have a real quick derivative rule. We know that d dx of tan inverse of x, remember this is the same thing as arctan of x, but I'm lazy, so I prefer to do one less pen stroke and do tan inverse instead of arctan. So this will be equal to 1 over 1 plus x squared. Now what I'm going to do is I realize, okay, well I wasn't working with f of x equals the derivative of this. So I'm going to integrate both sides to cancel out that derivative. Okay. So what I'm going to do is I'm going to ignore this integral for a little bit and just work on the 1 over 1 plus x squared. So 1 over 1 plus x squared, we know that has a power series representation of n equals 0 to infinity of, let's see, this should be negative x squared to the n, and then we'll have our dx. So this should be equal to the integral of the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n dx. Okay. So on the left-hand side, our integral and our d dx cancel out. So we'll have tan inverse of x is equal to, right, so I just worked on this piece right here. Now I'm going to work on this piece over here. Remember our integral rules, they say that we add 1 to the exponent of x and then divide by that exponent. So we'll get the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1. And then we'll divide by this new exponent. And then, of course, our plus c. Now let's say we want to find this c. Okay, well again, it's generally easiest for us to do let x equals 0. Showing off them cursive skills. And so we'll get tan inverse of 0, which is 0, is equal to, well now notice when I plug in x equals 0 right here for our summation, that x will become 0, so we'll get a 0 on top divided by constants that are non-zero. So this whole sum just turns into a sum of zeros, which is 0, plus c. And so that tells me that c is going to be equal to 0. So tan inverse of x is really just equal to the sum from n equals 0 to infinity of negative 1 to the n x times 2x to the 2n plus 1 over 2n plus 1. Okay. Now let's look at example 12. Example 12 asks me for a power series representation for f of x equals arctan of x over 2. Since all we're doing, remember last problem we did arctan of x? Since all we're doing is multiplying that x on the inside by a constant, what I can do is just multiply our x in here by a constant. Okay, So then we'll get that f of x is equal to the sum from n equals 0 to infinity of negative 1 to the n times, instead of x, we'll have x over 2 to the 2n plus 1 divided by 2n plus 1. So this is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, and then on bottom, we'll have 2n plus 1 times 2 to the 2n plus 1. Okay, so there's my power series representation for example 12. Oh, we're also asked to determine the radius of convergence. Here we're not going to, but generally, we see that we have a constant to an n power, so you can use the ratio test right here to get the radius of convergence. In fact, sorry, all of these determine the radius of convergence were meant to be practice problems, right? So this is practice from 11.8. So if you get to one of these and you can't get the radius of convergence, then feel free to come to office hours or ask me. All right, now example 13 asks us to do the definite integral from 0 to 1/3 of the function we just worked with. So first, what I want to do is let's just integrate what we had before. Right, so let's take this thing right here. We're just going to plug that in down here. Dx. And let's integrate it. So what we need to do here is add 1 to the exponent of x and then divide by that new exponent. So we'll have the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 2 divided by 2n plus 1 times 2 to the 2n plus 1, and then times our new exponent for x, so times 2n plus 2. Alright, now, since this is a definite integral, I'm going to put our brackets in here so that we know that we need to evaluate. So going from 0 to 1/3. Alright, so then this would be equal to, what I do is, just like regular definite integrals, we plug in 1/3 for x, and then we have a minus sign, and then we plug in 0 for x. So this is n equals 0 to infinity of negative 1 to the n times, remember x is now 1/3, so this will be 1/3 to the 2n plus 2 over 2n plus 1 times 2 to the 2n plus 1 times 2n plus 2. And then we'll have minus the sum from n equals 0 to infinity, negative 1 to the n times 0 to the 2n plus 2 over 2n plus 1 times 2 to the 2n plus 1 times 2n plus 2. Let me close that parenthesis off. Well, notice that this right here is going to go to 0, which means that the whole top is going to go to 0, which means that every part of this series is going to be 0. So this entire thing is just 0, so it turns out that our answer for this definite integral sits right here. All right, that will conclude our lesson for, what was this? 11.9.